Thank you very much for the introduction, in particular for the invitation, both to Alain and to the mathematical department. It's a great honor and a privilege to be in this room and to speak in this building. If you look at this slide, it's a familiar sight. It's a pebble beach, and many of the shapes on the beach look familiar. They are just pebbles. So here is a pebble. You would recognize pebbles. You would recognize this beach. However, if I would ask you to name some of these pebbles, that would be a challenge. We don't have names for shapes. We have names for very few shapes. And for the majority, you can see quite a number here. It's a couple of trillion pebbles on a medium pebble beach. We don't have names. And this might be related to the fact that linguistic skills and shape recognition skills are in different cerebral hemispheres. There were comments being made on this subject. One is due to Leopold Kronecker, who was a famous mathematician, and he said that God created the integers, all else is the work of man. Meaning that, well, in today's language, I would say you would like to, your bank account, you would like to be identified by an integer number and maybe not by a drawing. It's a safe thing. This is the thing, the integers are something where we feel home, where we feel comfortable with. And shapes are maybe a little bit more elusive. There is another famous citation from Galileo, which is well known, that the book of nature is written in the language of mathematics. However, the second part of that citation is probably less known. It says that the symbols in the book are triangles, circles, and other geometrical figures. So Galileo says that we need to understand shapes in order to talk about natural phenomena. However, if we need to understand them, we need to talk about them. And the first, if you want to give names to the shapes, the first thing is to assign integer numbers to these shapes somehow. So our goal is, in a broad sense, to understand natural shapes by using natural numbers. To what extent can we explain shapes by the means of natural numbers? There has been a lot of thinking about pebbles. So this is not the first attempt to describe pebbles. Aristotle wrote at length about pebbles, and he actually constructed a model, the evolution of pebble shapes. In brief, I would say that he predicted that pebbles are spherical. Well, as you saw in the picture, not every pebble is spherical. The pebble in my hand is not spherical, certainly. But there were other speculations. David Hilbert wrote his very famous book, Geometry and the Imagination, where he made a comment that coastal pebbles tend to be ellipsoidal. And in fact, if you go to the mathematical collection of Göttingen, which is a very famous mathematical collection, started in the 17th century, the first piece in that collection is a coastal pebble. So people were wondering about pebble shapes. Not much later, Lord Rayleigh, who is the son of the Nobel Prize winning Lord Rayleigh, pointed out that pebbles are not ellipsoids. So pebbles don't seem to be spherical, don't seem to be ellipsoidal. What are pebbles like? Do we have a name for pebble shapes? What are the numbers which we can use to characterize them? Well, the kind of numbers I'm interested in are related to mechanical properties of a shape. So here is a disk. And, well, I will, now this is a question, how shall I put it down? If I put it down, it is rolling along its perimeter. And there are positions where it would stand still. And there are other positions where I can balance it like a pencil on its tip. These are the stable points, and these are the unstable points. In a mathematical language, we can say that we describe this shape as a distance from its center of mass, and the maxima corresponds to unstable points and the minima to stable points. So in this way, we assign some numbers to this shape. And in 3 dimensions, we can do a similar thing. Here is, well, I take this pebble as an illustration. This is a kind of an ellipsoid-like pebble. It's not an ellipsoid. This can be also described as a distance function in 2 variables, because now we have 2 spatial coordinates, 2 angles. The minima of this function are stable points, where I put it down and it will stay like that. There are saddle points, and there are the maxima, the tip of the ellipsoid. So there are 3 types, and the numbers of these are related by a famous theorem by Poincaré and Hopf. So in 2 dimensions, the number of stable and unstable points is always equal, and in 3 dimensions, we have this relationship. Are these numbers, so to each pebble or to each shape, we can assign these numbers. Are they meaningful? Do they tell us something about nature? Well, to tell, I have to go back a little bit. Okay, to find the numbers, next time you go onto a beach, you will be tempted to do this. So you take a pebble in your hand, you find the stable points relatively easily, and also the unstable points and the saddle points are rather easily identified by a hand experiment. To motivate why these things might be relevant, let me briefly tell you the story of the Gomboc, which Alan already announced. And this goes back 25 years. I was visiting Cornell University, and my friend Andy Ruina suggested a very interesting problem, which is related to what I just told you. So here is, I think this is called a weeble. It's not in a good shape because my son, who is 2.5, is using it rather frequently, but I hope it will work. So you know how these things work. Yeah, there's a little music also. No matter how you put it down, it will come back to the same position. And have you ever taken a weeble apart? Maybe earlier on, and you don't remember, because my son is doing it all the time. So if you do it, you realize there is a weight at the bottom of the weeble. That is why it works. Now the question was, if we take a planar disk like this, and we are not admitted to add any weight to the disk. It is just a disk. And we roll it along the perimeter. So it is a 2-dimensional planar problem. Is it possible to cut out a disk so it behaves like a weeble? So it has just 1 stable point and 1 unstable point. Now, this question is easily answered, relatively easily answered. And let me briefly tell you how. So if we measure the distance, as I told before, from the center of gravity, having this weeble-like disk would imply that this distance function has just 1 maximum and 1 minimum, because then it would be behaving just the weeble, coming back always to the same position. Now, the idea is to disprove this by contradiction. So if we slice this function, the length of the slice is 0 here when it is tangent, and it is growing. At some point, the length of the slice will be exactly 180 degrees. So if we translate it back to the original body, we see that's a straight cut through the body. And we can see here that any radius inside the slice is bigger than any radius outside the slice. In plain English, not in a rigorous way, I could say that the body has obviously a fat side with all the big radii, and it has a slim side with all the small radii. Well, that seems to be a contradiction, because the body, if I support it under the center of gravity, it's supposed to be in equilibrium. It's supposed to be balanced. However, this body is not balanced along that blue line. It will tilt over to the right-hand side. So we got a contradiction. There is no such body. We called it a theorem because we were proud of it. We published it, and probably nobody ever read it. So it disappeared. A couple of years later, I went to a large conference in Hamburg, which is probably the largest ever mathematical conference with 2,000–3,000 people in attendance. And I went there primarily to see Vladimir Igorevich Arnold give the plenary talk. He gave a very interesting talk. He talked about various disciplines, optics, mechanics, geometry, and in each case, he showed that some number is equal or bigger than 4. Obviously, I saw that a little theorem, which was completely gone, proved actually that we had 2 stable points at least and 2 unstable points at least. So altogether, we had at least 4 points of equilibrium. So is this the same number 4 as Arnold was talking about, or a different number 4? I wanted to ask him after the talk, but that didn't happen. There were just too many people. So the organizers offered to the audience, if we pay a fee of 30 German marks, we can be seated with a celebrity of our choice, which was half of my weekly budget then. But I volunteered to pay it. I was seated with Arnold together with 15 other people, and everybody had to offer something. So the lunch was not very successful from my point of view. At the end, he asked whether I had anything to offer. I said no, because it was a painful scene, and he left. Many of you may know Arnold. For those of you who don't, at that point he was a little bit older than I am now, but he was already a small planet has been named after him. Sadly, he's not alive anymore, but we could list him as one of the significant, influential mathematician thinkers of the last 50 years. And so I got a little bit disappointed. I gave my own talk, which was in the wrong session, and just the chairman came and myself, and I left the conference. And that would have been the end of the story, but I noticed that Arnold was talking to someone, and he wanted to get rid of the person, and he told him that it's obvious what you are telling me, and by the way, I have an appointment with a gentleman over there. That was me. So he told me that I saw your name tag, you are from Budapest, you paid the 30 marks, so you must have a very good reason to come to that lunch. What is your reason? I got 20 minutes. You just tell me briefly. So I told him briefly. He was thinking about it. And I offered him to explain the proof of our little theorem. He said he knew the proof. He doesn't need that. And he asked, did you think about the 3-dimensional case? And I said, yeah, of course. We already solved the problem in 3 dimensions. So what is the solution? Well, you take this kind of body. This is a cylinder which you cut off like diagonally. How many stable points does this have? What is your guess? So how many positions would it be still? If I put down on this table, we will try it afterwards, where it would stand still even after I rock it a little bit. So it is really a stable equilibrium point.
Is that infinite amount?
You said infinity, which is a good guess. If it would be a cylinder which is cut orthogonally, yes, it would have infinitely many. But it is not cut orthogonally. It's cut at diagonal angle. 2, we are going down now. So any other guesses? Yes, sir. 4, now we are going up again. I am asking about stable. Stable. We will come back to that. 2 stable. Okay, anything? Anybody else? Just 1. So let me try this. I just put it down. And you can see it just comes back to the same position, no matter how I put it down. Okay? So it always comes back to the same position. It has one stable point of equilibrium. So Arnold was staring at me, and I was for a brief moment impressed with myself, because I saw that one of the leading mathematical thinkers, I could surprise him. He was genuinely surprised. But then I realized that he was not admiring me, it was more like pity. He said, you realize that this is completely wrong, what you are showing me. And I said, no, this is good. This is a good example. And I was so hungry that I was tempted to offer him to go to the buffet and buy a piece of sausage and make an experiment, hoping that he would pay for the sausage. But it never came to that. He told me that, OK, yes, it has one stable point, but how many altogether? Well, 4. It has one here at the tip. It's an unstable point. Another one here. And it has here, this is a saddle point. A saddle point is unstable in this direction, in almost any direction, but it is stable like this. So it has 4 points. So, young man, he told me, once you have something which has less than 4, you send me an email. But now I have to go. And so once he was leaving, I asked him, and do you think that this thing exists? And he said, well, I think many people try to prove that it does not exist, because there are many indications that it does not exist. But I think it may exist. So I went home and started thinking. So this is the summary of what I told you until now. In the plane, we have the same number of stable and unstable points, always. So it is sufficient to characterize one object with one of these numbers, because the other number is the same. And in 3 dimensions, we have 3 types. This object has 1 stable, 2 unstable, and 1 saddle. But it is sufficient to characterize it with 2 numbers, because the third one can be computed. So the problem is like this. In 2 dimensions, we cannot have 0, because that would be the perpetuum mobile. We cannot have 1, which I proved. And for any other class, we have an example, because for n larger or equal than 3, we have regular polygons, and for n equal to 2, we have an ellipse or whatever. In 3D, the situation is utterly different. We have a matrix, 2-dimensional matrix. This is my famous sausage. 4 and 4 is, for example, a tetrahedron, and Arnold was asking about this body. Now, Christopher Columbus was challenged once to balance an egg on its tip. This is an egg from the hotel. And if you put it down, it won't stand on its tip. You can see that on the camera. So what did Columbus do? Yeah, let me try that. So, and he won the bet or whatever. Now, in mathematical terms, what he did, he added a new equilibrium point. So it was used to be unstable. He turned it into a stable one, and he added other points around it. The main idea is that if you do small changes to a body like that, you can always add new points. And we can formalize this. It's not difficult to prove that if you have I and j stable and unstable points, you can always increase one of them by a suitable small truncation. This is what we call the Columbus algorithm. And it means that for sufficiently small specific truncations, if you have an object here, you can have an object here and an object here. Now, what does it mean for Arnold's conjecture? What does it imply? We still don't know whether it exists, but if it exists, the existence of this object would imply that any other type exists by this algorithm. Okay, so this algorithm is just telling you the significance of this object. Let me show you this. So here is, this is very important for this talk. So this is just a cuboid, a rectangle. It's a block. Okay. How many stable points does it have? 6, right? 6 stable faces. Now, here we chopped off 2 small pieces at the corners. And if I put it down on that face here, it falls down. So we did not, by chopping off this face, nothing happened. It is not a new equilibrium. If I put it down on this face, it stands still. So we added a new equilibrium, a new stable point. All the previous ones are still working. Okay? So by chopping off small pieces, you can add. That is the idea of the Columbus algorithm. Now, but we still didn't know how it works. What is the shape? So we went for holidays with my wife to Greece, and I convinced her that as an evening program we should collect pebbles and classify them according to the Poincaré-Hopf formula. To make this more scientific, we should probably collect 2,000 pebbles. Some people in this room do know my wife. And those who know her will not be surprised, but the others may be, that at 1200 I gave up, but she insisted that we finish the project. Now, this is the result. We did not find any shape. We didn't find any shape which had this property of Arnold. So we flew home. I got a little bit depressed because, you see, Arnold was a very, very significant mathematician, but on occasions he could be wrong, right? So maybe this conjecture of his was just wrong. It could be wrong. There is no evidence that it was good. At home, I started thinking, what could have been the reason that we didn't find this shape? And one is that one can assign flatness and thinness as a measure to convex bodies. There are many ways to define it. There is one particular way. So this is from Alan's office. This is the sphere. It is not flat and not thin. Nobody will dispute that, okay? So this has minimal flatness and minimal thinness. So we assign the values 1 and 1 to the sphere by this definition. I am sorry I didn't bring a frisbee, but most people are familiar with that. This definition would give a very large flatness and a very small thinness value. And for the pencil is very thin, but it is not flat. And what we could prove that if this object existed, it would also have minimal flatness and thinness like the sphere, but it would not be a sphere. So that would explain why we didn't find it on the beach, because things next to the sphere tend to be rather sensitive. So the idea which I showed you in the planar case sometimes works in 3D, sometimes does not. And starting from the case where it does not work, we produced an example of this surface, but it could not be manufactured because the deviation from the sphere was so small. Somewhat later, we came up with this shape. Here is the shape, and I thanked Alain for the invitation. I didn't thank him particularly for lending me his personal Gomboc for this presentation. This is a particularly nice piece. So we will need a little bit space here, but the egg. Yes. So here is a nice piece, and I let it move a little bit. So for this object, it takes a little bit more time to find its way back to the stable equilibrium. But unlike the salami, it has only one unstable point. That's a major difference. It's very hard to manufacture. So very small design errors lead to many equilibria. Like with a sphere, if you make a small perturbation, you get many equilibria. So we resolve the Arnold's conjecture. This is the first really well-working Gomboc. and we decided to give it to Professor Arnold on the occasion of his 70th birthday. This is the picture with Peter, with whom we constructed the shape. There are a number of pieces now around the world. We are most proud, of course, of the Oxford Gomboc, which is outside the room. Now a little bit of detour. So we looked at this shape for a while and realized that it is similar to some turtles. However, those turtles couldn't be found in Hungary. They were tropical turtles. So we had to go to the zoo and ask for permissions. It took a while, but so this is a Gomboc with a small error. And then I went to the history to the Museum for Natural History, and I was given a huge turtle shell of a leopard turtle. I put it down on the floor, and I saw that it had 16 different stable positions, and I knew this was an imperfect Gomboc. Now, we measured many shells, and we turned over many turtles, I am sorry to say, but we tried to do it so that with each turtle only once. And what resulted was an observation which probably more interesting to the scientific community than the Gomboc was originally, that many turtles self-right by muscle power. So they use their necks and arms and legs. So this is a very nice example. If you have aquatic turtle at home, don't try it many times, but you try it once, you will see it. Even large aquatic turtles can do this. And there is another technique which has been adopted only by 2 or 3 species. They came so close to this Gomboc-like shape that they self-right by gravity. So this is a main tool for them to survive, because being turned over is for a turtle a life-threatening situation. And medium turtles cannot self-right. Tall turtles found this shape or got so close to this shape that the biologists believed us that this is not a coincidence. Now back to the story. So this was in Moscow, and I gave this talk on the Gomboc. Professor Arnold was in the audience. Of course, I was a little bit nervous. He listened to it, and after that he said, this is a good job, but now we should do something else. And he outlined some problems which I didn't understand because I was too nervous. Later on, we met in the elevator, and he told me that he liked the talk, and in particular, the story, the pebble stuff was very interesting. And I thought he liked that our marriage actually survived this trial, but his interest was more mathematical. He asked, do you realize the significance of your slide? Well, for me, it had multiple significance. First of all, which I just mentioned, it's a memory to this event. But also the significance was that we didn't find any Gomboc piece. And he said, this is obviously not the significance of your slide. This is just the opposite. Put there 2 lines in your imagination at 2. So disregard the first row and the first column, because they might be disregarded for physical reasons, which I will just describe. And look at the rest. Look at the numbers. The Gomboc is not in this table, but it is almost there. It is almost there. It looks as though pebbles would be evolving towards the Gomboc. Now, this was very strange for me, really. And I hope it is also strange for you, because the first part of the lecture was about why this cannot happen. Let me just briefly describe about those white barriers. That is the easiest part. That is the easier part. Also, he told me that he didn't formulate as a conjecture. He just gave us this hint that maybe this is happening. And he told me that unlike the Gomboc, this is serious mathematics. So now you have to learn stuff. Okay? So this was his hint. And so abrasion for pebbles occurs in 2 ways. Either it is by friction, so the pebble is sliding. You can hear it. When you go to the beach, you can hear this sliding and rolling motion. If something is very flat and it is sliding, it tends to become even more flat. If something is very thin and it is rolling, it tends to become even more thin. So shortly, friction accounts for those barriers. Friction would accumulate things at either two stable or two unstable equilibrium points. However, certainly doesn't account for why shapes would move in that direction. That has to be driven by collisions. Now, as I showed you, if you take a collision, in a collision, which I will not do physically, a small piece will come off if I hit it very hard, okay? And what I illustrated before is that if we take off small pieces, the number of equilibrium points, apparently, naively, we think always increases. How is it possible that the opposite happens on the beach? Well, so naively, this is the evolution which is suggested by this model. So you take off a small piece and you get more equilibria. To take less, okay? Is it possible to reduce the number of equilibria? Yes, if you chop off a large piece. Okay, how can we chop off a large piece? We chopped off, say, this piece here. I show you an enlarged version of this piece. This is here, just you can see better, okay? It's the same thing. We can say that this is a rectangle where this has been chopped off, or we can say that this is a rectangle where this has been chopped off. And if we adopt the latter view, then how many stable points does this have? It's a tetrahedron. 4. So this has less. But in order to get there, we needed to chop off almost all of the body. So it's not clear what's happening. Now, so what we did, we made a computer simulation. We took a rectangle and we were chopping off diligently small pieces, and we counted the number of balance points. Here is the plot. So you can see initially it went up, then it went down, then it went up, then it went down. So how is that possible? Well, we said that in order to reduce in order to add the new points, the truncation has to be sufficiently small. But I never said what is sufficiently small. This depends on the shape. So in a natural process, the pieces being chopped off, let's say they are roughly constant. What is sufficiently small depends on the shape, and that may vary. And when this actual piece is below the curve, then the number of equilibria goes up, otherwise it goes down. So anything can happen. We don't have any prediction for the average. And in particular, the Columbus algorithm, this chopping algorithm, cannot be regarded as a model for a natural process because of this reason. Because in mathematics, when you say sufficiently small, you may mean very, very small. And in nature, collisions create, on the average, similar-sized collisions, similar-sized pieces being broken off. We can average also in space. So assume we have a ellipsoidal kind of thing, and we put on a very, very, very fine mesh. On that mesh, we will see equilibrium points, many of them, but they will gathered, concentrated in flocks. That can be proven. So they are always in small domains. Now, if we track the number of individual points, it may differ very much if we track the number of flocks. And indeed, if we track the number of flocks, we see that that is decreasing. Of course, we ran it many, many times, but this is the average. So the trend is that it is decreasing. So here is a real pebble. And if you scan it very carefully, you see the same phenomenon. On the surface of the pebble, you see many, many, many little equilibrium points, but they appear in flocks. So if you ignore the details, you see the good picture. So in order to get a sense of the phenomenon, you have to ignore the details. You have to ignore the small scale structure. There are two scales, and you have to think on the global scale. And the Columbus algorithm was very much on the local scale. Now, the models describing averaged behavior, so time and space averaged behavior, are called partial differential equations. And that is what Arnold was referring to. In order to find what is happening on the time and space average, you need to understand this in terms of these models, in terms of partial differential equations. They are called PDE models. What is a partial differential equation? Well, the kind of partial differential equation we are interested in is, imagine here is a curve, and at each point you move this curve in time, and at each point of the curve you define a speed in the normal direction, and then the curve shrinks. And then again the speed is given, and then again the curve is shrinking. So this whole phenomenon is a partial differential equation. Things depend also on space and also on time. As this curve evolves, first we have a certain number of equilibrium points, and in the end we have, in this case, we have less. So equilibrium points may disappear or may appear. If they disappear, we call it an annihilation. They went away. Or if new come around, we call it a creation. Both events can take place in this process. Now here are our questions. What is the formula for the speed which describes a natural aberration process? So what is the partial differential equation we have to understand? And if we find that formula, what is the average value for omega? Would it be positive or would it be negative? So Arnold's hint was in the direction that if you look at it in a very averaged way at the right equation, then omega will be positive. The average value of omega will be positive. Here is it in 3 dimensions. And well, I have some models here. So the easy way to study it, if you go to the drugstore and you buy a bar of soap, and then you wash your hands with it, you will see something similar happening. We did it the hard way. We modeled one of these equations with a computer and printed out in 3D what came out of this. So here are these successive shapes. We started with exactly this cuboid. Okay, this had 6 stable points. This is the next stage. And this still has 6. Although they appear to be a slightly less stable, so to say, but they are still 6. This is the next one, sometime later. This is stable. This is still stable, but I cannot balance it here anymore. So these ones somehow disappeared at the long ends. And this is the ultimate thing, which is a kind of an ellipsoid. It's not an ellipsoid. And you probably believe me that I can only balance it here, no other point. It will always fall over. So we started with 6 and we ended up with 2. So at least from the experimental or intuitive point of view, it seems to make sense that if we evolve this thing in an averaged way, we get rid of equilibrium points. Is it actually true? Can we say anything about this mathematically? Well, the formula, the actual equations for these aberration processes were there. Nobody read this paper. I think this is a brilliant paper, and it was written by Fred Bloor. He was in Liverpool. If anyone in this room knows anything about Fred Bloor, I would be grateful, because we tried to contact him. He's now retired, but we couldn't get hold of him. So he wrote this paper in 1977, and he laid down the geometric equations for pebble aberration. So he gave the right formula for V in case of collisional aberration. These equations are very, very difficult equations from the mathematical point of view. Very little is known about them. On the other hand, not known to Bloor there was a huge activity close to these equations, not quite these equations. So these equations tell you that the speed by which the boundary is moving inward is depending on the curvature. So more curved things move more speedily. And in 3 dimensions, it depends on the Gaussian curvature and the mean curvature, and there is a constant term. This is a rather complicated, I would say nasty, partial differential equation. However, there was some activity which was Bloor not aware of, and that was the Poincaré conjecture, which attracted enormous mathematical powers. And ultimately, the Poincaré conjecture was proved via the Ricci flow, and the Ricci flow is a generalization of this flow. This flow is a special case of the flows which Bloor has studied. So for this flow, it's called the curve shortening flow, the Poincaré conjecture, the proof for the Poincaré conjecture is one of the major mathematical breakthroughs of recent years, and it attracted top people. And that was a very lucky thing, because they were certainly not, okay, Bloor didn't say anything about annihilation or creation of critical points. He didn't study it. They were not interested in it either, but they were working on these flows for an extended period of time. They were studying the properties of this flow. There were surprising great theorems being proven about these flows, which I won't tell you today, but it's a very interesting topic. One of these papers by Matt Grayson showed that in the case of this flow, omega is equal to 1. So if you just take the planar curve and you shrink it by the curvature speed, the number of critical points is going down. Of course, this is a special case of that. And to generalize it, I had to put in some weakening conditions, assuming genericity of the bifurcation for the critical points. But taking these assumptions in addition to the original problem, for the planar case, based on Grayson's result, one could prove that omega is equal to 1. So always, the number of critical points is always decreasing. In 3 dimensions, the situation was much worse, because it is not true that it always decreases. Sometimes it increases. And I was stuck. I couldn't do with this term anything for a couple of years. Then I discovered that there is another equation which is much better understood than these very special geometric equations. That is the heat equation. The heat equation is describing the dissipation of heat or in a medium. It was written down and first studied by Fourier. And later on, in the 80s, it turned out that the heat equation is a good model for the blurring of images. This is a very fashionable topic. And that started an industry of studying of the features, of the geometric features of surfaces evolving under the heat equation. Now, there was a huge literature on this, and even in 1995, it was an open question whether in the heat equation, which again is a much simpler equation than Bloor's equation, whether creation could occur or not. It was an open question, and James Damon finally showed an example where creation could occur. But people were not satisfied with that, because if they looked at the screen, most of the time they didn't see it. They see annihilations, but they didn't see creations. So 2 mathematicians, actually students of Köndering, said that the term which we cannot explain, we will replace by a random variable with 0 expected value. And if we do that, then we get a random process, the expected value of which is positive. Now, the same can be done for the more complicated case for the Bloor equations. So what it adds up to that the discrete process suggested an evolution in this direction, but from the averaged models we get an opposite indication, but only in a random, in a weak sense. So it is moving that way, but not maybe, not always, but most of the time, I would say. Okay, let's go back to this chessboard. These are the stable points, number of stable points and number of unstable points. All that we need from all the previous mathematics is this. Assume we have an object in here and we are throwing a dice. But the dice is not correct. It's more often it is falling to this side. The dice will determine whether the object will move up, to the right, down, or to the left. And because the dice is loaded, that is what was derived before, it's more often that it would go up to the left than it would go to the right and below. That's a very simple statement. And in each, of course, we have the barriers due to friction. And this process, so we have many, many objects, and we are throwing these dice many, many times. The simplest assumption is all these probabilities are constant. This is a very simple model. It's a very simple, it's called a Markov process. And it is very well understood. And it gives you a distribution. If you start with many particles all over the place, it gives you a very definite distribution for the end results. It will be a stationary distribution. And if you compare that with the field data which we had on the Greek island, you see you get a very nice agreement. So this process is a very particular process. So you start it with an initial value, so you take a bunch of pebbles, you take the average number of stable and unstable points, so it is not an integer anymore, and you start evolving this process. So what you will see, that there is a fast descent, and then it starts to roam around in some area. So there are definitely two phases. The first phase is a diffusion process which has a drift, and the second phase is a recurrent process. So let me show you some data. The first is what I would call coastal data. So we've collected many, many, many pebbles on many, many coasts. It's a good scientific activity. So I am planning to apply for a grant to extend these activities to many other coasts. These were collected privately, so to say. We collected each of those little circles means 50 or 100 pebbles. Some of them were less abraded, some of them were more abraded, smoother. And if we start this very simple model from the less abraded pebbles as initial values, the trajectories seem to go to the right place. So they seem to find the pebbles which are more abraded. Maybe, but there is no causal relationship. We collected these pebbles in many different locations. So it is not true that one of them was abraded from the other one. Now this is Australia. This is a small, not a small, a medium river in southwestern Australia. And we sampled pebbles along the river in 12 places. Here you can see some pictures from the river. And here is the plot. Now, if you run this Markov process here, you get a trajectory which is reasonably close to the data. And if you run another trajectory, it is still close to the data. So there is a fast descent, and then there is some recurrent process. Another example, always go to tropical places, as you notice. This is Puerto Rico. And actually, colleagues had a grant to go there every year and sample pebbles, and they had a lot of data, but it was not so meaningful. And we proposed that include the number of equilibrium points among the stuff which they measured. So we also offered that one of us would go and help them. So they accepted this proposal. There are actually two rivers here, a tributary and the main river. And here is the plot. And again, you can see that there is a part where it is descending, the number is descending very fast, and then it seems to be oscillating. And if you go to a lab and run this experiment, you just put in number of pebbles in a drum and rotate it, and you measure the number of equilibrium points, you cannot get it wrong. So it is the process is so stable, so robust, that there is no way you can get it wrong. You always get a similar process. So this seems to be a true natural process. The mathematical statements which I made could be made probably more rigorous. Oh, here's the lab data measured. So as a summary, I might say that next time you go to a nice pebble beach, think about this, that pebbles, maybe not every aspect of pebbles, but some aspect of pebbles, the story about pebbles can be told with natural numbers. Maybe only a small slice of the story, but it is a true story. It's certainly happening. So this is what Michael Berry summarized, is that the Gomboc exists in nature, but only as a dream. So all pebbles, deep down in their heart, they want to become a Gomboc, but few manage. Thank you very much for the attention.